In our last lesson of this chapter, we're going to take a look at transformations of exponential and logarithmic functions. And I know thinking about graphing these is making you so happy inside. However, I'm thinking the fifth time that we've seen transformations, and the last time we saw it, you guys did really well, so don't panic. You know this. This is all information we've already seen. So as a quick review, our first function, the exponential, b to the x power. Domain is all real numbers. You can raise any number to any power. However, the range is y is greater than 0. So what I want you to have in your mind as we're going through these transformations is what the parent function of all exponentials look like. And it's something like this, if the base is bigger than 1. So this, our y-intercept, is 0, 1, because for the parent function, the most basic form of an exponential, b to the 0 power equals 1. So we're going to be focusing on the intercept as well while we graph. And the asymptote is the x-axis, or the equation y equals 0. So for our log function, again, notice that the domain and the range flip, because the x and the y values flip from a parent function, from a function to its inverse. So our domain is x is greater than 0, because you can't put a negative value into a log, because you don't get a negative value out of an exponential. The range is all real numbers, because the answer for a log is the exponent, and you can raise any number to any power. Asymptote is our y-axis, or x equals 0. So what I want you to have in mind when we're graphing our log functions is what the parent function of all logs looks like, something along these lines. At the bottom here is the summary of transformations for exponentials. They've got a summary on page 538 of the transformations for logs, but they're all the same. And again, all of this you already know. If you are adding something to a function, that's a vertical shift. If you are adding or subtracting something grouped in the asylum with the x, that's a horizontal shift. If you multiply the function, that's a vertical stretch or compression. If you're multiplying the x, that's a horizontal stretch or compression. If you multiply the function by a negative, that's a vertical reflection. If you multiply the x by a negative, that's a horizontal reflection. All of this you should be going, yeah, we know this, move on. So let's move on. First, we're going to describe the transformation of our function. So looking at it and kind of thinking order of operations, we multiply before we add. So I'm going to look at that negative e to the x. We're multiplying the function by a negative. If it's outside the asylum, it's vertical. So we have a vertical reflection. And then the plus 4, the 4 is positive, so it's up 4. Next, we're going to give the equation of the asymptote. Have the parent function of the exponentials in your mind. The x-axis is the asymptote, or y equals 0. But we shifted it up 4, so the asymptote goes up 4 as well. So y equals 4. Domain is still all real numbers because we didn't mess with the x. The range, we did mess with the range, so to speak, in two ways. We shifted it up 4, and we reflected it vertically. So instead of being y is greater than 4, we have y is less than 4. It flipped over the asymptote. And finally, the y-intercept. So think about the parent function of the exponentials. The intercept was 0, 1, because anything to the 0 power is 1. So for minus 1, then would be 3. So two ways, lots of ways you can think about it actually. We reflected it to negative 1 and then added 4 to get 3. Or you can just think about substituting 0 in for x and evaluating to get 3. All right, so now what we're going to be doing is actually sketching these graphs. It's not going to be real precise. We're not going to make a t-table. I want you to think about the asymptote, think about the intercept, and think about, in this case, the reflection to get an idea or a sketch of what the function looks like. So I'm going to plot my y-intercept. I'm going to do a dotted line for my asymptote. I know that it was reflected vertically, so I'm picturing in my mind, instead of going up and to the right, it's going to go down and to the right, approaching this asymptote, but never actually crossing it. So there's a quick sketch of what this function looks like. All right, now we're going to take a look at the transformation of a log function. So we're multiplying the log function by 3, so that is a vertical stretch. And we grouped with the x a -1, so that's in the asylum, so that's not normal, so we actually shifted it right 1. All right, equation of the asymptote. I hope you picture that log function in your mind. It's got the y-axis as the asymptote, and it grows gradually off to the right. Since we shifted it right, the x equals 0 gets shifted right as well. So our new asymptote is x equals 1. The domain, we did mess with our x, so the domain changes as well. The domain of the parent function is x is greater than 0, but we shifted that right, so now it's x is greater than 1. The domain of the log function is just like the domain of a radical. You can't take the square root of a negative, and you can't take the log of a negative. So another way to think about that is x minus 1 has to be greater than 0, and then solve that inequality. The range, we didn't mess with the y values. We stretched them vertically, but that doesn't change the range. Just makes it grow faster. So our range is still going to be all real numbers. And the x-intercept. The x-intercept is where y is 0. Remember the x-intercept, I just realized I didn't put that on this one, and this looks terrible, but it's 1, 0 because it flips from the y-intercept of the exponential. So substituting 0 for f of x and solving for x, if you want to think about kind of doing it the long way, dividing both sides by 3 doesn't change our 0. And then we're going to convert this to exponential. 4 to the 0 power is 1. Adding 1 to both sides, we get an x value of 2. Another way to think about that is that we shifted it right 1. So that ordered pair that was 1, 0 went to 2, 0. So plotting this, and it's a vertical stretch of 3, so when I graph this, it's going to grow a bit more quickly than our log functions do. So keep that in mind when we're coming to our stretch. But again, this is just a sketch. So we've got our asymptote, and then our function will be stretched 3. So again, that doesn't look like the parent log function because it grows faster because of that multiplication by 3. All right, one more graph, and then we'll be done for this video. But there's a couple more topics we're going to look at. So this time we're looking at the log function. We multiplied the x by a negative, so that first transformation is a horizontal reflection. And we shifted it up 2. All right, equation of the asymptote. So for the log function, the y-axis is the parent function, asymptote, and because we didn't shift it left or right, our asymptote didn't shift either, so it's still x equals 0. The domain, we messed with our x values, we made them negative. We reflected it horizontally or across the y-axis. So the domain of the parent function is x is greater than 0. Because we flipped it, we've got x is less than 0. Range is still all real numbers. And our x-intercept. So thinking about the fact that we shifted it up 2, actually this one is going to get a little bit messy if we substitute 0 for f of x. To solve for our x-intercept, we subtract 2. To cancel the natural log, e to the negative 2 power, and dividing by a negative. So in order to graph this, we need to have an approximation for what negative e to the negative 2 power is. And sketching this function, so that is going to go in here. We still have our asymptote along the y-axis, x equals 0. It was horizontally reflected, so we have this baby x-intercept, and up 2. So this is the point we have. and actually that's, I graphed it like it's a stretch. It really should be a much more gradual curve off to the left, but we're just doing sketches, so that'll work for now.